benzoic, and the last one will be tertiary. Okay, so based on what the information I provided for you, you already know this is going to be your worst candidate because I'm putting a positive charge in the double bond. So immediately I know this is going to be dead last. It will be number 5, and that's it. Now what about the rest of them? So if you remember, the transfer of carbocation stability in SM1 is going to be tertiary, secondary, and lastly primary. And remember, resonance is the most important factor in determining the stability of a carbocation. So any of the substrates that have resonance are going to be the best ones, meaning this one and this one are going to be 1 and 2. So let's go ahead and look at which one's going to be 1, which one's going to be 2. This one's tertiary and benzoic, this one's tertiary and benzoic. However, this has only one ring to resonate the positive charge onto, and this will have 3 different rings to resonate the positive charge onto. Therefore, because it has more resonance structures, this should be number 1, and this should be number 2. So let's take a look at the remaining ones. None of them are resonance stabilized, and based on the trend that I provided for you, since this is tertiary, it will have more stability compared to this one. Any questions on part A? Okay. Okay, so part B is asking me to rank by SN2 reactivity. Now, remember, a little note. When I'm asking you to rank by SN2 reactivity, remember this equation. Your SN2 reaction depends on both your substrate and your nucleophile. So, I may be saying rank by SN2 reactivity, like determine nucleophilicity or substrate stability and so on. However, that information might not always be provided for you. So it is your job to determine which one is being asked. For example, in this case, am I asking you to rank by nucleophilicity strength or substrate stability? See, if you pay attention, all of these guys, well, almost all of them, are going to have a negative charge with them. Remember, when you see these alkali metals, potassium, sodium, lithium, always remember to cross them off and just replace them with a negative charge, because this is signaling that this will just be a spectator ion in your solution. So basically you have a negative charge on the sulfur, on this phosphor, on this sulfur. And based on that, I know my nucleophiles, if they have negative charge, they're going to be strong nucleophiles. So based on this information, I know that I'm ranking by nucleophilicity strength. I don't have any leaving groups here. Any good leaving groups, as a matter of fact. Alcohols are horrible, and these guys won't be as stable as your bromine, chlorine, and so on. So, since I'm ranking by nucleophilicity, let's take a look at what I have. So remember, the transfer in nucleophilicity is going to be left and down on your periodic table. So, if I were to write down your elements, this is what I will have. Right now, I'm playing with these 3. Or, okay. Oxygen, sulfur, and phosphor. So let's take a look at this. So between all of them, I know that the ones that are negatively charged are going to be the best nucleophiles. So that would mean this guy and this guy should be ranked the lowest. Now between an alcohol and an ethiol, which one will be worse? Well, here's the thing. Please memorize this sheet. I cannot emphasize this enough. Please memorize this sheet. See, based on this, I already know that this is going to be a good nucleophile versus my alcohols. So I already know that my alcohol is going to be number 5 because it's a weak nucleophile. So that would mean that this alcohol should be number 5, and the thiol should be number 4. Now from here, let's go ahead and compare the 2 sulfurs and the phosphor. So right now, I'm comparing these two elements together. Now the difference between my sulfurs is basically going to be whether I have a secondary nucleophile or if I have a primary nucleophile. Remember, your SN2 reactions are stereospecific. You want no steric hindrance in your substrate, you want no steric hindrance in your nucleophile, you don't want those. Therefore, because of that, this will be less reactive than this in your SN2 reaction. So that would mean that this should be number 3, and this should be number 2. Now between your phosphor and your sulfur, just look at the trend. I said that if you go to the left and down, you're going to have better nucleophiles. Since phosphor is behind sulfur, I know this will be number 1. Any questions on part B? Nothing? Okay. Let's take a look at part C. So, what's going on? Go ahead.
Can you re-explain what you meant by stereospecific?
Good question. So basically what I'm saying stereospecific, I'm implying that I don't want any hindrance. For example, compare this leaving group and this leaving group. So remember, in your SN2 reaction, the nucleophile is going to be coming from the backside. It's going to make a backside attack. So it will be attacking from this direction. Okay? So because I have 3 methyl groups and each of them have 3 hydrogens, they're going to be repelling the nucleophile. They won't be allowing it to react. Compared to this guy, where you only have 1 methyl group. Does this make sense? Excellent.
They want you to explain why you gave number 4 as.
Number 4. Okay. Number 4 compared to 5 or like 3, 2, and 1?
Yeah, I think 2 number.
Okay, good question. See, what I was saying is, remember this. Sulfur is beneath oxygen. Okay? So therefore, sulfur is automatically going to be a better nucleophile compared to your oxygen. And also, according to this sheet that I was talking about, here your thiol is ranked as a strong nucleophile, but your alcohol is a weak one. That's how I knew this was going to be a better nucleophile compared to your alcohol. More questions? Anything? Okay. All right. So part C question 1 is asking me to rank by E2 reactivity. So if you remember, the product of my elimination reactions, E1, E2, is always going to be an alkene. I'll be adding an additional bond. I'll be forming a double bond. So that would mean that once this leaving group leaves, this one leaves, and this one, and this one, and this one, I would have to form a double bond. So remember, in this question, I'm asking you to rank by alkene stability. It might not always be given to you straightforward. You might be given a question that says rank by alkene stability, but sometimes it will be implied. It won't be as explicit. So for example, in this question, remember, your alkene stability is going to be based on the number of substituents that you're going to have. So the more substituents I have, the more stable my alkene will be. For example, if I have 4 substituents on my alkene, that will be the most stable versus 3 substituents. And then once you enter 2 substituents, here you have to divide them up. In your double substituted alkenes, your stability trend will be trans, more stable than geminal, more stable than cis, mono, and lastly, well, no substituents. Geminal means that you have 2 substituents on the same carbon in an alkene, versus cis that you have 2 substituents on 2 different carbons, however they're on the same side. So, for example here, if you pay attention, I've given you bromine on a dash and the methyl on a dash. So when I'm trying to do an E2 reaction, remember, especially on a ring, I want the leaving group and the adjacent hydrogen to be transdiaxial to each other. Transdiaxial. Meaning that when I draw my chair, the leaving group, let's say bromine, for example, and the adjacent hydrogen have to be trans, meaning going in opposite directions, and be axial to each other. So on this question, I know that if I draw this chair out, since it's on a dash, I want the bromine to be going away from it. So I'm going to choose a carbon that allows me to make it axial. Let's say, for example, this one. So that would mean that this methyl has to be on the edge, and this methyl will be equatorial. So that would mean the axial hydrogen will be going up. So that would mean that the alkene I will be forming will have 1, 2, 3, 4 substituents. Does this make sense? Okay. Let's go ahead and check this one. So here, I've given you a methyl group. Now, if you pay attention, I didn't indicate stereochemistry for you. So I'm leaving it up to you to determine whether it's wedge or a dash. Try to take the most stable alkene. For example, put both of them on the same direction, like this one. Because then that will mean your hydrogen should be in the opposite direction of your bromine. Like this one. This one is dash, and this one was dash. That's why I could put the double bond right here. So that would mean once this guy leaves and I form a double bond, I will have 1, 2, 3 substituents. And then here, if I take off my bromine, my adjacent hydrogen is this guy. So if I form my double bond here, I will have 1, 2 substituents and geminal. And then here, if I take off my bromine, my adjacent hydrogen, either one works, doesn't make a difference. Let's choose this one. Will be this one. So I would have 1, 2 substituents, cis, and then the last one. So what's odd about this one? Can I even form an alkene on this thing? Exactly. I can't even form an alkene here. So automatically I know this should be number 5 in terms of E2 reactivity, because I can't even form an alkene here. This is a methylic substance. Sorry about the horrible handwriting. Okay, so based on this, let's go ahead and rank. So I told you 4, 3, 2, and here I've given you the trend, so let's take a look. This one's the only alkene that has 4 substituents, so this should be number 1. And then the next one is my tri-substituted alkene, so this should be number 2. And then both of these guys have 2 substituents, so I'm comparing geminal and cis. Since geminal is more stable, this should be 3, and this should be 4. Okay. Any questions on ranking by E2 reactivity?
Can you?
Okay.
That was 3 and 4.
Yes, yes, yes. See, this one, since this substituent and this one are on the same carbon, they classify as a geminal alkene. But here I have 2 substituents on 2 different carbons and on the same side. This classifies as cis. Go ahead.
So we should draw the chairs for like whenever we're doing like ratings.
Yes, definitely, definitely. Draw your chair configurations for your E2 reactions. If you're trying to do an E2 reaction on chairs, you want them to be transaxial. Definitely draw your chairs. Okay. Questions? Okay. All right. So question 2 is asking me to assign E or Z configuration to my alkenes. Okay. So when you're trying to assign E or Z configuration, remember, E means I have trans alkenes, and Z would mean I have cis alkenes. You can use both of them for your alkenes, but because E and Z is specific to alkenes, not just rings or any other compound, we try to use E or Z for alkenes rather than cis or trans. Now, when I'm trying to determine which substituents to take into account, think about it in terms of determining chirality. Remember when you were determining highest priority groups, when you're trying to assign RS configuration, it's kind of going to be the same thing. So I'm going to be choosing the highest priority substituents on either side of my alkane, for example. The highest priority between these two guys, the highest priority between these two guys, and so on. So for example, let's solve this one. For example, let's say I'm trying to determine the highest priority on this carbon. So if I move one carbon away, I have carbon, carbon, no difference so far. Carbon, carbon, no difference so far. And then I have carbon, nitrogen double bond, carbon, phosphor double bond. So because phosphor is going to be your heavier atom, on this side of your double bond, this will take priority. Okay? Now let's move to this side. So again, I'm going to be doing the same thing. Let's take a look. If I go here, I have carbon, carbon. So this carbon is attached to carbon on the ring, 2 hydrogens. This carbon is attached to carbon on the ring, chlorine and hydrogen. So I know this will be higher in priority. Now, if I pay attention, these two are on different sides, so they should be an E configuration. So basically, all I'm looking for is highest priority groups on my alkane. Let's take a look at the next one. So on this one, on this carbon, I have double bonded carbon attached to nitrogen, double bonded carbon attached to carbon. So immediately, which one is going to be higher in priority? The nitrogen or the carbon? Nitrogen. Yeah. So this will be higher in priority. So I know I'm looking at this one, even though this has the longer chain and it has a density ring. Next one. So here I'm looking at double bonded carbon attached to carbon, double bonded carbon attached to sulfur. So again, based on the same reasoning that you gave me, this will be higher in priority. So again, on two different sides, this will be E configuration. Even though this too has a longer chain and it's attached to nitrogen, we don't care because immediately I'm looking at what's immediately attached to this one, directly attached. And then if it's the same, I'll look at what's behind it. Okay. Last one. So here, I have a hydrogen attached. I automatically know this will never be the highest priority group. So on this side of the double bond, I know this will be higher in priority compared to hydrogen. Now what about this one? Let's take a look. So here I have carbon attached to carbon, carbon. It's the same. Let's go back. Carbon attached to carbon, carbon attached to carbon, the same. Carbon attached to hydrogen, carbon attached to nitrogen. So I know that on this alkene carbon, this will be higher in priority. Now, because these two are on the same side, I know they will be having a Z configuration. Any questions on question number 2? Go ahead. This one? Sure. See, on this one, I'm just doing the same thing. I'm looking at both sides of my double bond. So here, I know I have one hydrogen attached, so I don't care about that. I know that's going to be the lowest in priority. So this one's going to be higher in priority on this side of the double. Let's look at this side. See, whenever you have the same atoms, look at what else is attached to them. For example, here, carbon, carbon, same thing. Let's look at what else is attached. Carbon, carbon, and then this carbon is attached to hydrogen, hydrogen. This carbon is attached to hydrogen, nitrogen. So I know this side of the double bond, this substituent will be higher in priority. Make sense? Okay.
Why isn't the oxygen side the higher priority?
Which one?
The one with the oxygen on the example we just did.
Yep.
Why isn't the one with the oxygen, why isn't that one higher than the nitrogen?
That's a good question. Even if you took that into account, it will still be a Z configuration. Go ahead.
Is neither not an option
Which one?
for these questions? Does it have E or Z?
It has to be E or Z, yes. Yeah, here's. If it had to be neither, then, I mean, let's say I gave you 4 substituents that they were having the same priority. Then you could say like 9. Okay? But I don't think you'll be given something like that because they want to see if you can determine if it's E or Z. Okay? Good. Questions online? Anything on? All right, so let's take a look at question 3. So this question is asking me how many chlorinated products each of these substrates will give me. Now in these questions, your monochlorination products, remember, chlorination is less selective compared to bromination because chlorine is more reactive compared to bromine. Now, because of that, you could have multiple chlorinated products compared to, let's say, one brominated product. Now, the most stable product will be the highest yield. Nevertheless, you'll be forming other products. So in these questions, remember, you're always looking for a line of symmetry. A line of symmetry will allow you to eliminate answers that will give you the same number. For example, let's look at this one. Over here, I have a line of symmetry going down this way. So if I'm trying to determine chlorination, I'm going to ignore one half of the substrate. It could be either the right half or it could be the left. So I have this carbon available, this carbon, this carbon, this carbon, and this carbon. So for this one, I have 1, 2, 3, 4, 5 carbons available for chlorination. If I were to count these guys, it will be a repetition. Now, let's take a look at, let's say this one, for example. I can't form a line of symmetry here because these two substituents aren't the same. Neither can I form here, or here, or here. Since I don't have a line of symmetry here, I'm going to have to count the carbons that can account for a chlorine. See, your COOH, remember, looks like this. So this carbon cannot form any chlorine. I can't have a chlorine here. I can't break this bond off. So this carbon is off. Your CN is going to look like this. So I can't put any chlorines on here either. So this guy is off. Now, with this information, that will mean that the 5 carbons on this cyclopentane are going to be available for chlorination. So I have 1, 2, 3, 4, 5 carbons available for chlorination. Any questions so far on how I'm doing this? Go ahead.
Yeah, so for the third drawing, you said that there's 5. But
Yes.
shouldn't there be 6 between the first one and second one through? There's still a carbon at the top of the cyclopentane.
Here?
Yeah,
Good question. How many bonds does this carbon have?
got 4.
So,
Nice guy.
does it make sense? Yeah. So I can't break the CC bond. Remember, if I'm making radicals in your chlorination, bromination, I'm forming radicals. You're breaking CH bonds, not CC bonds, not CN bonds, and so on. So because of that, I can't put anything in. That's why I skipped it. Good question. Okay. Now, let's take a look at this guy. If you pay attention to this one, my line of symmetry is going to be right here. So I will have 1, 2, and then T-butyl, and here I'll have 1, 2, and then T-butyl again. Now, remember, this carbon isn't available for chlorination, so I'm not going to be counting this one. This one's off. So the ones that I will be counting will be this guy, 1, 2, 3, and 4. Therefore, on this one, I will have 4 chlorinated products. And then the last one. Do you remember that on this question, I said that you can't put a positive charge on your double bond. If you do, it's incredibly unstable. The same principle will be true for radical formation. You don't want to put radicals on your double bond, just like you don't want to put positive charges on your double bond. Having them be next to it, that's good, because that will mean it's resonance stabilized. Now, with that in mind, let's go ahead and take a look at this guy. So on here, I don't have anywhere to put a chlorine. Double bonded carbon, double bonded carbon, this entire ring is double bonded carbon, double bonded carbon. I cannot form any chlorinated products on this guy. So if you see double bonded carbons, cross them off. Don't even consider them. Don't even think about them. If you have this ring, for example, don't even look at it. Don't bother with this one. So for this one, I will have 0 chlorinated products, no chlorinated products. Go ahead.
Is another way to rephrase the question basically asking like, how many chemically different hydrogens do you have?
That's an excellent question you could ask. Yes, exactly. See, that's a concept that you will be approaching in OChem 2. When you're learning about spectroscopy, you learn about chemically different hydrogens. That's exactly the reason why. Questions? Okay.
Find the last one again, please.
So move on to the next page. All right. Okay. So here, I'm given the substrate and asked to draw the 2 major products expected in the following reaction. Okay. So it's saying I'm going to have 2 major products. Remember, I'm using NBS. So this will be N-bromosuccinimide. You don't have to know the name, just be familiar with NBS. NBS is signaling to you that you're doing allylic bromination, meaning that I'm choosing allylic positions. In this case, it's going to be this one. Now, if I resonate it, this double bond will move here, and then the radical will be here. That's why the question is asking me to draw the 2 major products. Okay, so if I were to draw them, the first one is going to be this position. Remember, I'm doing bromination. Bromination is more selective than chlorination, so I'm choosing the most stable location on my compound. In this case, it's going to be the allylic position. So I'm just going to put the bromine right here. Now, let's say I form my radical, this guy resonated here, I formed the double bond, the radical was here, then I could put the bromine here. So I could either have this guy, or I could have double bond move here, radical was formed here, so I could have the bromine formed there. Any questions on part A, question 4? Go ahead.
So why is bromine not also on the tertiary carbon?
Which one?
Is that the tertiary carbon?
Yes. This one?
Yeah.
Good question. Because resonance is a factor that contributes more to your stability compared to just having electron donating groups. Remember, you're comparing inductive effects and resonance. Resonance is going to be making your compound much more stable compared to just having electron donating groups.
So if we were asked to draw like all the possible ones,
Mhm.
would that count?
The tertiary position?
Yeah. No.
Remember, bromination is more selective than chlorine. You'll be forming the most stable products. Okay? For example, if this was chlorine, let's say this was like 75%, this was, I don't know, something else and something else. And see, the percentage will still hold for different positions. However, it will be higher in yield for the most stable one. Bromination isn't like that. You'll be forming 90-something% on this one and almost nothing on the other ones. That's why we discard the other products. Okay. And also, NBS is for allylic bromination. So this is another hint that told me I'm doing allylic bromination. Any other questions? Okay. Now here it says circle the product that will react with an AOH in an E2 reaction. So it's asking me which one will be doing an E2 reaction. Remember, in your E2s, you'll be forming an alkene. So between this one and this one, remember, your mechanism for your E2 reaction, if I draw a sample, let's say this guy, will be like this. E2, like SN2, is going to be a one-step reaction. So the same time that the leaving group is leaving, the base is going to be extracting an adjacent hydrogen. It's going to be extracting the hydrogen that gives me the most stable alkene, the Zaitsev product. So in this case, it will be this one. So when the bromine leaves as Br minus, I'm left with a positive charge. When the hydrogen is taken off, I'm left with a negative charge. The result will be the alkene I was talking about, resonance forming between these two guys. Questions?
Was it the first one or the second one?
Which one?
Which one of the two is it?
Okay, I'm gonna get to it. See, let's take a look at this one. I'm looking for hydrogens to take off and leave a charge. See, if I were to take a hydrogen off of this carbon, see, this carbon is vinylic. Even if I took this off and formed a double bond here, I will be forcing the structure to break. So my ring will break and the stability will basically go down. You will have a very, very unstable compound on that point. That's why you won't be even taking off a hydrogen from this location. And on this carbon, do I even have a hydrogen to take off? No. That's why it's going to be this one, because this hydrogen is available for me to take off. Yes?
Who is the first one? Where was the double bond formed in the interior?
This one?
Uh-huh.
LBD. Yeah. You can't do it like this. Remember, if you have two double bonds in the same molecule, it's going to be a linear structure. That's why I'm going to have to, I will be having to break this ring. Okay. There you go.
So taking hydrogen from a vinyl carbon is really bad.
Yes. You don't want to do that. Especially if it's in a ring like this. Okay. It says draw the product that will be obtained if the other structure reacts with CH3OH. So by other structure, I'm looking at the one that I didn't circle, this guy. Okay. So let's draw that thing out, the second product.
Hey, John, could you explain part B again? That you explain
Well, this one? Okay.
part B after you know that.
Okay. I'll solve this one and then I'll explain. So let's say this is reacting with CH3OH. So let's take a look at this compound. Now, over here, my bromine is secondary since it's next to two carbons. However, this carbon has two methyl groups attached to it. So it's the same as saying if this bromine looked like this. Now have this information in your mind. So this is secondary. And my nucleophile, is this a good nucleophile or a weak nucleophile? Yes, it's going to be a weak nucleophile. In order for you to do an SN2 reaction, you should have both a good substrate and a good nucleophile. Not having one of them, any of them, only one of them, will mean that you will never be doing an SN2 reaction. If you have a bad substrate, fantastic nucleophile, you're not doing SN2. If you have, let's say, a good substrate, a bad nucleophile, you won't be SN2. You're doing SN2. You need both factors in order to do an SN2 reaction. So already I know that I'm not going to be doing an SN2 reaction. So this is off. Now, CH3OH, methanol, on this list is telling me that it's both a weak nucleophile and a weak base. Remember, your E2 reactions require a strong base in order to proceed forward. Therefore, I won't be doing an E2 reaction either. So I'm stuck with an SN1 reaction. Okay? So the first step in my SN1 reaction will be to form my carbocation. Remember, SN1 isn't a one-step reaction. It isn't a concerted reaction. It's a two-step reaction. Step number one, leaving group leaves. I'm left with a positive charge. So I'm forming a carbocation intermediate. And then my job is to stabilize this positive charge before my nucleophilic attack. Now, if I were to stabilize this, I could either do, let's say, move this methyl here, do a methyl shift, move this here, or I could move this positive charge here. Now, here's the thing. Over here, my carbocation is secondary and resonance stabilized. If I resonate it here, it will still be secondary and resonance stabilized. Okay? So I haven't accomplished anything by moving it. If I do a methyl shift here, sure, I'll be making it tertiary, but I won't have resonance anymore. So that would mean that this position is already ideal for me to put my nucleophile on it. So with this in mind, I know I will be doing a similar reaction on this carbon. Okay, so let's say nucleophile attacks. Voila. Questions on how I did this reaction? Yes, go ahead.
Why did you use this second structure in the first question?
Oh, because the question was telling me, use the other structure, the one that I didn't circle, yeah? Yeah, it was saying use the other structure. That's why I need to use that one.
Thank you.
Yeah, sure. Questions?
Okay, just go for part B again.
Oh, yeah. So, part B. It was saying that circle the product that would react with NaOH in an E2 fashion. So remember, I told you that your E2 reaction, you're forming an alkene, and also, remember, I'm forming the double bond between the carbon that has the leaving group and an adjacent carbon. So my options would be this one and this one. I'm not counting this one because both of them are chemically equivalent. They're two methyls that are the same thing. So on this one, for example, I choose this hydrogen to take off because it will give me 3 substituents instead of 2 substituents. Okay? Now this was just an example. So here, let's look at this one. If I take off this hydrogen on the double bond, I'm placing a temporary charge. Remember, this is all very fast. However, that charge will be placed on the double bond. Okay? And also, even if I proceeded with my reaction and formed the double bond here, remember, having 2 double bonds on the same carbon would mean you have a linear structure. So that would mean I'm putting a lot of strain on this ring, breaking this bond off, making this extremely unstable. So this carbon is off, and on this carbon, I have no hydrogens to take off methyl. So here, I can't even do an E2 reaction. So that would mean this is my only viable choice. Okay? So it says, draw the rate determining step of monochlorination. Remember, when I'm trying to brominate, chlorinates, put halogens on my hydrocarbon, I'm forming radicals. The step that requires radical formation is going to be the highest in energy. So let's say initiation, I formed my BR radical, so I have this guy right here. I broke off the bromine bonds. What's going to happen is this bromine radical will now be approaching your second compound. So this guy is going to be looking for a CH bond to break. Remember, bromine-bromine bonds are much easier to break compared to carbon-hydrogen bonds. Carbon-hydrogen bonds, if you break them, you need a lot of energy to break them. So automatically I know that a CH bond breaking is going to be the highest in energy. Therefore, that's the rate determining step. So this guy breaking this way, and me forming, let's say, HBr, and the second radical is going to be my rate determining step. Yes?
How did you know to like move that double bond?
Which double?
Like you initially put the double bond.
Oh, sorry, I made a mistake in my drawing. Thank you for bringing that up. I apologize. Yeah. You're right. So I'm breaking this hydrogen bond. Sorry, sorry, yeah. My mistake, I apologize. Yeah. Okay, so I'm breaking this hydrogen bond instead, this way. So that would mean that double bond is staying where it is. I'll be forming my radical this way. Yes. Monobromination? Bromination, just adding one bromine onto a compound. The same thing we did here. This is monobromination, for example. Same thing as? Yep. Monobromination, one bromine, putting one bromine in this compound. Which one? This one? Yeah. Good question. Because if you remember on this one, I said that your most stable position is going to be this one. Remember, since I'm doing bromination, bromination is more selective. So I'm going to be choosing the most stable spot, and that's it. So the most stable spot was this one. Therefore, this is the CH bond I'm breaking to put bromine on.
Isn't the formation of HBr really like unfavorable?
Yes, you're right. However, the problem is, even though HBr, well, this is going to be unfavorable, I'm still forcing my reaction to proceed. I'm giving it heat. That's why when you're doing Br2, when you're doing bromination, you're adding light, you're adding heat, because it's an endothermic reaction compared to chlorination. Yeah.
Wait, I have a question.
Yes.
So for the radical, you broke that down. Was the break was the double bond?
Double bonds right here. I didn't touch double bond.
So you're breaking that and the hydrogen? to
So
make
I'm
that-
breaking a carbon-hydrogen bond, basically. See, on this question, based on the answer I provided in part A, I knew that this was going to be where I will be placing my bromine. So I knew that my radical would have to form here. So I knew that the CH bond I'll be breaking is this CH bond.
So you're breaking that and then moving it to the next carbon? Is that what you're
See,
saying?
this means, see, I did a half arrow. This is say that I'm breaking this bond, so hydrogen is going to be moving away as a radical, and instead we'll be bonding with my bromine radical. So I'm forming HBr, and this carbon will also be forming a radical.
Okay, so you're not touching the double bond.
No, 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 I'm not doing anything with the double bond. Okay. Good. So, question E is saying, what does the structure of the molecule look like in the transition state? So I'm giving two options. Does it look like the reactant or does it look like the product? Now you might be asking, well, how should I tell? So I don't know if you discussed this in your class or not, but you have something called Hammond's postulate. Hammond's postulate basically says that if I draw my reaction energy diagram, let's say for example this one, let's say my reactant is here, and the product will be here. So this is right now an endothermic reaction. Depending on where your transition state is, where your peak is, if it's closer to your reactant or if it's closer to your product, I can tell that at the moment, the structure right here looks more similar to my product compared to the reactants. Yes?
Can you repeat D just one more time?
Which one?
They were saying that your audio cut out for a second, so they wanted you to repeat.
Question B or D?
But you-
D, okay.
the one you-
So for D, it was asking me to draw the rate determining step of monobromination. So like I said, the rate determining step is the step that has the highest energy. Just like you pointed out, it's going to be unfavorable basically. So you need a lot of energy. So I knew that in bromination, breaking carbon-hydrogen bond is going to be the highest in energy and therefore my rate determining step. So I drew this carbon-hydrogen bond getting broken by the bromine radical. So this is what I was drawing. Okay. And back to this one. So bromination is going to be an endothermic reaction compared to chlorination. So this will actually be your energy diagram for bromination, Br2H mu, compared to chlorination, where I start here and end up here. So I know that because this peak, this transition state, is closer to my product than it is to my reactant, the structure over here at this very moment is more similar to the product than it is to the reactant. Does it make sense? Any questions?
How did we know it was that graph versus the other one?
Which one? Oh, you should know this. Bromination is endothermic, okay, compared to chlorination here. Because chlorine is more reactive. So you don't need to put as much energy, expend as much energy to force this reaction to go forward compared to this guy. Okay. Any questions before I move to question 5? All right. Let's do question 5, and then we'll do like a 5-minute break, 7-minute break for you all to, I don't know, grab a snack, drink water, use the restroom, anything. So question 5. What does the structure of the major product look like if this molecule reacts with KOH? So let's go ahead and draw this to KOH. Okay. So remember, whenever you're trying to determine what reaction to do, SN1, SN2, E1, E2, always begin by looking at your substrate and determining whether your leaving group is on a secondary carbon, primary carbon, tertiary, and so on. Always begin by this. So over here at the moment, let's take a look. This bromine is on a secondary carbon. Remember, when you're trying to determine what reaction you want to do, I personally am looking for a way to always either do SN2 or cross it off. It's because I know my SN2 reaction needs both a good substrate and a good nucleophile. So I know if I have both of them checked off, I'm doing SN2, and if one of them is off, I'm not doing SN2, it's crossed off. Okay? Now in this case, I have a secondary carbon, and in your substrates for SN2, the trend is methylic, primary, secondary. Basically, secondary is going to be your last step, your last chance for an SN2 reaction. Because for tertiary, you will never be doing an SN2 reaction. So right now, I know that because this bromine is on a secondary carbon, it's going to be a good substrate. Okay? Any questions on this one? Now, there's something that I'm not pointing out for you guys. Pay attention. This is secondary, yes. However, I have a bulky group right next to it. So even though this is a secondary compound, and you might say, well, this is secondary, it's a good substrate, it's next to a bulky group. And remember, your SN2 reactions are stereospecific. They don't like steric hindrance. This will be acting as steric hindrance for you. That's why I know that this won't be a good substrate. Okay? So since this is off, I'm not doing an SN2 reaction. SN2 is off. Now from here, I'm going to ask myself, is this a good base? KOH. Okay, good. So here, KOH, if I dissociate it, it's going to be giving me K plus, OH minus. OH minus is both a good base and a good nucleophile. So because of this, because I have a good base, I know I can do an E2 reaction instead. If this wasn't a good base, I'll be stuck with an SN1 reaction. Any questions on this one? Okay. So since I'm doing an E2 reaction, there's something that you have to take into account. your leaving group and the hydrogen you're about to take off have to be anti-coplanar with each other. They have to be anti-coplanar, okay? Now, this bromine is on a wedge going up, if I look at it this way. Oh, sorry. Like this. That would mean that my hydrogen is on a wedge going up. Remember, anti-coplanar would mean that in my Newton projection, if I were to draw it for you guys, the leaving group and the hydrogen should be exactly opposite to each other. So that would mean, for example, this be on a wedge going up, this be on a dash going down, or you could have both of them be on lines going opposite directions. You could do either one. Either one works as long as they're anti. However, I personally like to do this way because this would mean that any substrate I have attached to this carbon is either on a wedge or a dash. So if I draw my alkene, I know which substrates, which substituents are going to be in the same direction. Whatever's on a wedge is going to be on the same side. Whatever's on a dash is going to be on the same side as well. So let's go ahead and take a look at this thing. So right now I have this. What I want to do is turn this bromine this way. So it's on a line. So let's say I'm looking at this thing right now. So right now, bromine is going to be this guy right here. But can everybody see this? Okay. So bromine is going to be this red ball, and methyl is going to be the white ball down here. So if I rotate bromine this way for it to be on a line, that would mean that I'm putting the methyl group here on a wedge coming towards me. So that would mean that the hydrogen here is going away from me. Okay? Now, let's go back to this guy. So right now, the hydrogen is on a wedge coming towards me. So I want it to be going down on the line. If I take this down on the line, that would mean that the secondary butyl over here would have to be on a wedge coming towards me. So I would put this here, and then this would mean that this methyl group has to be on a dash going away. Now, this will make my job easier because once I draw my alkene, I'm just saying arching for this big thing already. So if I draw my alkene, I know that the arching and the secondary butyl will be on the same side. And the hydrogen, which I'm not going to draw, and the methyl are going to be on the same side. Let's say it's here. You don't have to draw this hydrogen. So arching is basically this guy over here. Questions on this one? Yes.
How did you get the line diagram? Like, how did you decide which? Doesn't what I'm trying to say is, doesn't that hydrogen need to be on the other side for it to be anti-coplanar?
On this one or this one?
Yeah, and the first one.
This
How
one?
did you get to be on the other side of it?
Good question.
Or
See,
keep the hydrogen and bromine on the line.
good question. Good question. See, it will be fine if you put the hydrogen on a dash going down. You could just rotate one carbon, right? That's fine. You can do that. That's fine. However, I personally like to do this because that would mean once I draw my alkene, it's easier for me to determine which substituents are going to be on the same side. See, for example, here I knew that the R chain and the secondary butyl will be on the same side because both of them were on a wedge. And here, the hydrogen and this methyl group over here were going to be on the same side because both of them were on a dash. So I put both of them on a line because it was easier for me to determine the substituent positions at the end product.
You basically did invert it, like, the whole thing?
Yes, I rotated both of them.
Did you have to? Do you have to? Because isn't the, like, the original one, isn't it
Mhm.
already intercoplanar?
No, it isn't. See, the hydrogen and the bromine are both facing the same direction. They're both on a wedge going up. They will be anticoplanar if one of them was on a dash going down, exactly the opposite. Yeah.
So what were the products?
Your R chain is basically this segment.
So you can't draw it on the ring? Or like,
I can draw it out. I was just being too lazy. So
sorry.
I'm gonna draw it. So let's say it goes carbon attached to carbon, carbon attached to ring. So it will be this way like this. So this way like that.
So the final product has the double bond between the bromine and
This way?
the right there.
Yes.
That's for the one.
Yes. Because yeah. Go ahead. Go ahead.
If we drew it like this, is it wrong?
Okay, so that will mean, right now you put the methyl group and the ring on the same side. See over here, I put secondary butyl and the ring on the same side. See, that's why I did this. Because I knew these two were going to be on the same side, the R chain and the secondary butyl, because both of them were on a wedge. Yes?
Why is there a line
Which one? A line?
yeah, where the double bond is made?
Uh-huh.
There's a line, there's a methyl there, but didn't that go?
Where? This is the methyl group over here.
Like on the double bond,
Uh-huh.
like on top of it. And the final drawing. Like,
Yes, yes, yes. So this is the methyl. Yeah.
Double bond is on that connection rather than the top of the one.
See, good question. See, there's a hydrogen here and there are two hydrogens here. If I put the double bond on this location, I will have 1, 2 substituents. If I put the double bond here, I would have 1, 2, 3 substituents. Remember, I'm always choosing the more stable alkene, the more substitute alkene, which is known as your Zaitsev product. The Zaitsev product will be formed this way. If I put an alkene here, remember, I'm forming both of them. However, your Zaitsev product will be the highest yield. So this will be a Hoffman product if I were to draw a double bond application.
Putting a double bond right there
Mm-hmm.
between the VR and the dash.
Yes,
Is that wrong?
like that. Well, see, when you're drawing your double bonds, you're not really indicating wedge or dash. See, over here, I didn't do that either. Yeah. So doing that, you have to show which ones are going to be on the same side, which substituents. You showed me that the methyl and the ring were on the same side. The answer is the secondary butyl and the ring are on the same side. That's why I did this inversion. That's why I did anticoplanar.
the problem that I have is like looking at the original thing, like on that ring, there is not a hydrogen, like where that like, whatever that bulky like methyl is.
Mm-hmm.
That one, like that doesn't have, like if you draw it on a chair, there's not a hydrogen that's going to be axial.
On a chair? This is on a ring though. I'm not doing each one on a ring.
Okay, so basically, that's what I was thinking, the hydrogen is not going to be.
See, think about it like this. When you're doing an E2 reaction, you're looking for an adjacent hydrogen to take off, right? So my options are either this guy or this guy. If I form the double bond here, I would have 1, 2 substituents. If I form the double bond here, I will have 1, 2, 3 substituents.
So because it's not a ring, it doesn't matter if the hydrogen has to be down.
No, no, no. See, on a ring, transdiaxial translates to anticoplanar on a regular line angle diagram.
You don't have to worry about this.
No, you have to worry about anticoplanar instead of transdiaxial.
Yeah, that's what I was thinking. So you can.
You don't need a Newman projection for this one. Yeah, you don't need a Newman projection because how are you going to indicate an alkene on a Newman projection?
Yeah, that's what I was saying, but they wanted you to do it.
Okay. Questions? Yes. Could you speak a little bit? Sorry. Which dash? This one? See,
And make it a wedge.
if I were to rotate the dash, I would have to rotate the entire carbon. You can't just choose a substituent to rotate around. See, I can't just rotate these two together, for example. I can't just rotate these two. I would have to rotate this entire thing. See, I would have to rotate this thing. I can't just switch these two around. I mean, if you rotate your substituents, you have to rotate the other substituents as well. That's what I'm trying to say. So if this becomes a wedge, then that would mean this goes on a dash, for example.
Okay, so there's 3 things attached to that carbon that you can.
3 things. Yeah, one of them is a wedge, one of them is a dash, one of them is going to be just regular line, on a line.
But there's only 2 things, that's why you can't. There's only 2 things, that's why you can't.
2 things like an alkene. Yeah. See, on your alkene, you don't have bond rotation. You have 2 bonds strictly bonding your 2 carbons together, so you can't rotate them. Yes.
You draw a Newman projection.
Yes.
And make it anti-cosilinear,
Uh-huh.
and you draw the product. You get the same answer.
Yes. Yes, you will. However, why would you need a Newman projection? Because you can't indicate an alkene on your Newman projection. That's why you didn't draw it.
You try zooming in.
Zooming in. Which one?
Oh, they're just saying it's hard to see.
Better? You should have told me that from the beginning. Okay. Right. Yes. Which one? This way? This one?
Yes, you just turn it to the left. You have to correct that.
Turn this to the left. See, this entire thing is counting as steric hindrance.
Yes.
Yeah. So it doesn't make a difference. Yeah, the entire thing is here. If I rotate it, it's still like a big block for you.
So you still, then you wouldn't be able to draw double bond.
A double bond or an SN2 reaction?
The double bond.
Okay, see, steric hindrance is only for your SN2 reaction.
I know, but
Okay.
I'm asking about visualization of that.
Uh-huh.
So
Okay.
what I'm asking is that part, if you just turned it over like this,
This entire thing?
yeah,
Okay.
would that work?
See, if I rotate the entire molecule, oh, rotate this carbon.
Yeah.
Oh, yeah. See, if you could rotate this, yeah, that's what I just said. If you rotate this in a way that puts the hydrogen on a dash going down, you're fine. You're good to go. I did this type of rotation because it told me where my substituents would be. Wedges are on the same side, dashes are on the same side. That's why I did this type of rotation instead of that. Okay? Yes.
How did you get the like in the first one, the oxygen thing was, how did you get the whole like the shape to change from like the original problem? Because like in the answer your oxygen is sort of like it's a different shape, and then like the substituent is going into like a different direction, and then like how did you get the whole? Like, how did you know how to orient that?
It's the same thing. It's the same. No, it's the same shape. Yeah. See? It's the same shape. It's the same thing.
So like in this first one, like the double bond is not in.
Come here, come.
I never claimed to be like an English major. So. Okay,
See,
this is what I meant. Like when I drew it.
oh, you're
I
comparing
kinda-
these two?
Like
Both of them are
how
fine.
you like this is what I drew, but this is what like
Oh yeah, I indicated line angle.
yeah.
And also, you have a problem. The methyl group and this group are going to be trans to each other, not cis. So this is wrong.
So how do you know to make it trans?
That's why I did anti-coplanar. That's why I did the rotation.
Okay, I'll just ask you about it tomorrow.
Okay. Who wants to take a 5-minute break? Go ahead. Go ahead. Go ahead. Take it. If you have questions, I'll answer them. Keeping up with the I'm good. I'm good. Thank you so much.
I know. Would this be a score? That was which one? For like
This
it's good.
which are that is if it's on your double line, you
Oh, you only said it's on double bond.
yeah. See, both of them are on the line since on.
Okay.
Because your sp2s, those are sp2 hydrogens, right? They're going to be like a flat surface. So you have nothing on the
Right. Okay. Yeah, I have a couple other really small questions. So on these things, I don't know. I just wanted to curious. How do I know what element is attached to this carbon over here?
Oh, that's a little my fault. You see, it's going to be carbon. That's what I was thinking. It's going to be carbon. Okay. That's a little mine.
But still, at the end, we're just comparing, obviously, that carbon, the fact that carbon is attached to phosphorus versus
Exactly. I'm comparing phosphor and nitrogen.
Okay. And then here, over here, whenever you're doing it like this, would the negative charge be on the hydrogen or the phosphorus?
Phosphor, definitely. Because that sodium is basically attached to it. Phosphor is essential atom.
Oh, so it's on the central atom. Okay. Gotcha. Perfect. That's everything. Perfect.
I just on the same question. So if I just show,
That's okay.
so if I didn't want to show here, would it be right if I just did, if I just did stereochemistry?
It's absolutely okay. As long as you want to saying which substitutions are
So if I do it like this, it's a little hard to hear.
this is problematic because your methyl and the ring are on the same side. So then the answer says you're trans to each other.
So I have to
Rotate this carbon.
so put this on the other side.
That's why I do it this way,
Okay,
because
okay.
it tells me which is on the same side. That's just on the same side.
Okay. Thank you.
Remember, these methods, all three of them are the same thing. Yes, so I only count this. No, we don't know that. Yes. What? See, bulk group stereochemistry is in the context of an sp2. Hoffman is basically saying you're forming two alkenes, right? You're leaving representing the adjacent to two carbons. Okay? The carbon that you choose, the highest substituted alkene is going to be giving them the right. But if I take a less substituted alkene, I'm going to use Hoffman. So when you're using a bowl, like
Well, I was with her.
oh, it's the same question. Okay. This is a problem. See, if you put a double bond, for example, this carbon and this carbon next to a benzene, you're making it fun. That's excellent. So here, I can give you a slide that
So that's what I did for these, which I got right, but these two I mixed up.
yeah. because here, tertiary, see, I look at it in terms of alkene substitutions. Here I have four substances, three substances, 2, 2, 9. Now between the twos, I know the trend was going to be geminal, for example, trans-geminal.
So, where would you have to be?
Chair configuration, when I'm doing cyclohexane, that's why I do this. Make sense?
This is recorded, right?
Yes, yes, yes. Don't worry. It's just a sign.
Oh yeah. They keep start off with really projection.
If I do new one, I'm not helping them out.
Exactly, that's what I've been trying to tell them, but like they say they might be expected to show it anymore, but you can't.
Yeah, exactly. How are you going to show double bonds between a front carbon and a back carbon?
That's exactly what I was saying. But they still have some doubt.
I'll do at the end. I don't want to get behind.
I was gonna say.
Sorry, I just wanted to clarify. Wait, so I got up to this part, and then that's when I got out the alkane, and I saw that oh my gosh, not gonna ask. Both of these are up. So I was wondering how you got the trans confirmation for the metals, if that makes sense.
Yes. See,
Sorry, you want to pencil?
no, it's okay. I have it. Yeah. See, these two, I know the R chain and this thing, since they're both on a wedge, they're going to be on the same side. They're going to be cis with each other. The
Oh
wedges.
my gosh.
And the dashes are going to be cis with each other.
Okay.
Like that. That's why I did it this way, because this tells me which substituents are on the same side.
That makes sense.
Yeah.
Thank you.
You're welcome. Okay. All right. Okay. All right. Which one? Oh, this one's working. What about now? It is on. All right. Can we get back to the questions? Okay, so 5B is asking me the structure of the major product I would get if I were to react the same structure with LDA. Okay, now here I was reacting with KOH, and here I'm reacting with LDA. Now, both of these are going to be strong bases. However, the difference is that LDA is going to be a bulky base compared to KOH. So whereas this is also a good nucleophile, this is only a good base, not a good nucleophile. Remember, your LDA, I mean, I don't think you have to know this, but I'm just going to draw it for you. Looks like this. This counts as a bulky base. So when I'm using LDA, KOTBU, any base that is bulky, I will be forming a Huffman product instead of a Zaitsev product. So whereas here I was choosing this hydrogen to take off, on this one, I have to choose this hydrogen to take off because I'm using a bulky base like LDA. So I will be forming a Huffman product instead. So if I were to do the same procedure, let's see. For example, here, right now the bromine is on a wedge, hydrogen on a dash, and then I have this thing. And here I have hydrogen on a wedge, hydrogen on a dash, and then this attached to the ring. So, yes. You okay? Yeah, okay. Okay. So here, all I'm doing is just rotating it this way because I'm going to be forming my alkene. So remember, again, since I'm doing an E2 reaction, I have to have my leaving group and the hydrogen be anti-coplanar with each other. So if I do that, if I rotate this, let's say bromine is on a line going up, that will mean hydrogen will have to be on a line going down like this. Okay? Now, if I indicate that the bromine right now, over here, is the red ball, hydrogen is the white ball, and this big hydrocarbon chain is the dark ball, what I'm going to be doing is, I'm going to be rotating this way. So based on this, the bromine is on a line going up, line going up. Then I'm going to have hydrogen on a dash going down. So that will mean that this big chain is going this way. And then let's go back to this one. Let's say on the back carbon. These two small balls, the green and the white one, are the hydrogens, and this is my R chain. So what I want to be doing is be turning this around. That will mean that the R chain will be on a dash going up. So the hydrogen should be, the second hydrogen should be on a wedge. Now remember, this bromine is reacting with this hydrogen, not this one. So I do it this way because this tells me that when I form the double bond, this substituent and the hydrogen are going to be on the same side. This is the benefit of rotating both carbons instead of just rotating one of the carbons. See? Wedge, wedge, over on the same side. And then here, the R chain and this hydrogen are going to be on the same side. See, this one has 1, 2 substituents compared to 1, 2, 3 substituents. This is the Hoffman product. This is the Zeitzek product. That's the difference between them. Questions? Yes. Yes, because I'm using LDA. If it was the same with potassium tertiary butoxide KOTBU, that would be the same thing. Okay. Now, part C says what would be the major product if this molecule reacts with ethanol. Remember, like I told you, my alcohols, ethanol, methanol, propanol, they're all going to be weak nucleophiles and weak bases. So I won't be doing SN2 or E2. So I will be doing an SN1 reaction instead. So if I were to draw your product, let's say here. If I were to do the reaction, I would have the carbocation forming here and the methyl over here. Okay? So remember, my job is to stabilize this positive charge before doing the nucleophilic attack. So you might be tempted to move this carbocation here because it makes it tertiary. However, here's the thing. If I move this carbocation here, it's going to be resonance stabilized on the So because of that, I know that the carbocation should do a hydride shift onto this carbon instead, since it will be able to resonate onto this ring. So if I do the nucleophilic attack with ethanol, I should have this. This should be nice. Any questions on this one? E1C. When you're looking at an E1 reaction, it's more of a specific reaction. E1 is when I'm reacting an alcohol with a strong oxy acid, like sulfuric acid, for example. That's when I'm doing an E1 reaction. So if you pay attention here, I was determined between 3 reactions. I don't have any E1 here. Questions from this page?
So is it also okay to call it, I know you said it's resonance stabilizer, but is it the same thing to call it allylic?
Yeah, it is allylic. Because it wasn't on a benzene, so it's not benzoic, but yeah, it is allylic. Correct. Correct. Okay. Whatever. So this is what I wanted to get. I haven't seen your exam. I don't know what will be on your exam, but I am guessing you're going to have a large portion dedicated to reactions, determining whether it's SN1, SN2, E2, E1. I haven't seen your exam. I'm just guessing. So for this question 6 is basically asking you, determining if it's SN1, SN2, E1, E2, and then draw your product. So for example, here, I will be looking at my substrate. On all of these examples, I'm going to be looking at my substrate first, always determining if it's primary, secondary, tertiary, and so on, and then moving on to what's on the arrow. Okay? So here specifically, remember I told you to always cross off any alkali metal you see and replace them with a negative charge. Sodium, potassium, lithium, cross them off, replace them with a negative charge. So in this case, I have H minus. So far, you've been used to seeing H plus react. H plus is an acidic hydrogen. This is a basic hydrogen. Okay? So in this specific reaction, this basic hydrogen will be looking for an acidic hydrogen to take off and extract as H2. Now, here, the most acidic hydrogen right now looks like this. Okay, so if this H minus takes off my alcohol's hydrogen, I'm going to be generating an oxide, an O minus. This is going to be acting as a strong nucleophile. Now remember, this chlorine is on a secondary position, and this oxide over here, this alkoxide, is going to be a strong nucleophile. So I have a good substrate and I have a good nucleophile. I will be doing an SN2 reaction. However, the thing about this reaction is that you have both your nucleophile and your leaving group on the same thing. See, your nucleophile isn't on an arrow here. It's present here. So if this oxygen attacks this position and takes out the chlorine, remember, since it's an SN2 reaction, I will be doing inversion for my stereochemistry. So this oxygen will be bonded to this carbon. That will mean that I'm forming a ring here. This is what you refer to as intramolecular SN2, meaning that your SN2 reaction occurs within the same compound. I'm not using an external nucleophile. The nucleophile is within the compound itself. So over here, the oxygen is going to be attached here, and I will have a 1, 2, 3, 4, 5, 6 member ring. So if I were to draw this out, that would mean that this carbon, because I'm doing SN2, it's an inversion stereochemistry, this should also be on the dash, attached to the oxygen instead, because oxygen is taking chlorine's place. And from here, I'm going to determine what my ring will look like. So 1, 2, 3, 4, 5, 6, 7, like this. Yes. So remember, this oxygen will be attaching to this carbon, right? Okay. So my ring will consist of this carbon, 1, 2, 3, 4, 5, 6. I didn't say 6 carbon ring. I said 6 member ring. Yeah. It's actually a 5 carbon ring. Yes. Go ahead.
So for the chlorine, it's a secondary
Mm-hmm.
substrate.
Yes.
It's also hindered, right? Because the carbon right next to it is attached to 3 carbons.
Mm-mm.
A
No.
lot of carbons.
Here.
Yeah, that's a hindered carbon, right?
If it was tertiary, it will be hindered. On the previous example, the E2, I said it was hindered because I was using a secondary butyl group and a methyl. that group itself, the secondary butyl, was considered large. Here, this is a linear compound. I don't have any branches coming off of it. That's what I'm trying to point at. If this was tertiary, sure, it will be considered hindered.
Not a tertiary.
No?
Because it's connected.
This carbon is attached to 1, 2 carbons.
This carbon is now considered.
Which one? See, this carbon specifically is attached to 1, 2 carbons.
What about
The chain? Oh, the chain is just part of your nucleophile. No, I don't count it. Yeah. Yes.
So the reason the oxygen kicks out the chlorine is because of the basic hydrogen?
Yes. The basic hydrogen extracted the alcohol's hydrogen. So this guy right here. This got extracted. So basically, let me retry. I had this. The H minus extracted the hydrogen. So I ended up with an O minus. Okay. Yes.
Can you explain how you do it with SN2?
Oh, yes. See, I always begin by looking at my substrate, whether it's primary, secondary, tertiary, and so on. So here, I had a secondary substrate, right? Now, you might initially think, well, alcohols are weak. Here's the thing, alcohols are weak. But because I'm using NaH, and H minus will be making this a good nucleophile. So I have a good nucleophile, and I have a good substrate, so I'm doing it. Questions? Yeah.
Can you on a wedge instead of the dash because the
Which one?
conversion,
Yeah.
Wherever the top where the oxygen is, shouldn't that be a wedge?
See, the chlorine is on a wedge right now. So that would mean my nucleophile should be on a dash, just like I indicated here.
And on the bottom, shouldn't it be a wedge?
No, this isn't getting attached. This isn't getting attacked by any nucleophile.
So we only care about the chlorine basically.
Yes.
I mean, like, that's why we should.
See, if this position was getting attacked, let's say we were doing an SN2 here, then yes, whatever was attaching would be on a wedge position. But here, only the chlorine is getting attacked in an SN2 reaction. Okay. Next one. So over here, remember, this question is telling me that my first step I'm using AgNO3, and on the second step I'm using this alcohol. Okay? So my substrate right now is on a primary carbon. However, this carbon is tertiary. And also, even if I disregarded my substrates, this alcohol is both a bad base and a bad nucleophile. So I can't do an SN2 or an E2 reaction. Yes? Yeah, it is quaternary. That's what basically I was pointing at. I was saying primary next to tertiary. It's just like saying quaternary. Yeah, you're right. It's the same thing. Same thing. Primary next to tertiary is the same as quaternary. It's hindered.
It's just quaternary.
Yeah. I got into trouble to last like 2 semesters ago by telling a student this was quaternary instead of saying primary next to tertiary, because one of the instructors apparently didn't like that. That's why I use both of them. Yeah. I say primary next to tertiary or secondary next to tertiary. It's the same thing. Yes.
Doesn't the AgNO3 like force an SN1 reaction?
Yes. I was getting to it. Yeah.
Is this like a reason?
Yes, it is. Yes, it is. See, on this one, because I'm using AgNO3, I'm automatically indicating that I'm going towards an SN1 reaction. And also here, this is a weak nucleophile and the weak base. So both of these guys are indicating to you that you're doing an SN1 reaction. Okay? So that would mean that the first step in my SN1 reaction is always and always going to be formation of a carbocation. So I'm going to form a carbocation here. Now here's the thing. Right now this carbon, it is under extremely large angle strain. Okay? So in your SM1 reactions, let's say I'm given a 4-member ring or a 5-member ring, or in this case, a bridge carbon, a single bridge carbon as a matter of fact. These guys are going to be unstable. So in your SM1 reactions, if you're given the ability to ring expand from a 4-carbon to a 5-carbon, or a 5-carbon to a 6-carbon, or just expanding your bridge carbon, take that opportunity. This will give you a more stable compound as a matter of fact. Also, this carbocation right here is primary. It is unstable. And this carbon right here is attached to 1, 2, 3, 4 carbons. So that would mean I have nothing here to shift on this guy. So the best way to stabilize this guy is by doing a ring expansion. So what I can do is break this bond off. So I'm breaking this guy off, and I'm reforming a bond here. Okay, I broke this guy off. I'm reforming a bond here. So if I were to erase it, let's see. My new bond will be forming this way. So I end up having this. Remember, this is one of my bridge carbons, and now I'm introducing a second bridge carbon to this. But because I broke the bond here, I'm introducing the charge on this carbon. So this ring expansion allowed me to take off angle string and put the carbocation on a tertiary position. So now this is ideal for an SM1 reaction. Now I can do my nucleophilic attack. So I will have this. Questions on this part B?
So how did you know how to redraw the like bicycle compound, like from the whenever you broke it, you formed the bond? Like how did you know how to redraw that?
See, I knew that I'm breaking this bond. Okay, so I showed it again. I broke this bond off. So when you break this bond off, this will have a negative charge, this will have a positive charge. So these two are going to be attached to each other. So I know that these two will be bonded to each other. These are the same carbons that I drew here. That's how I know both of them will be bridge carbons. Yes? Yes. See, right here, if I take off my leaving group, the bromine, if I take this off, I will have my carbocation forming on a primary carbon, right? And also here, I don't have anything to shift it with, not a hydrogen, not a methyl, nothing. However, I am given the opportunity to expand this. And by doing so, I'm putting this carbocation on a tertiary position, which is much more preferred for an SM1 reaction. Okay, that's fine. So, C, I'm given an alcohol, and also I'm given tosyl chloride. Remember, alcohols are not good leaving groups. They're horrible leaving groups because if I take them off, I will end up with OH minus. Over here, your OH minus is a strong nucleophile, so it is extremely reactive. Therefore, you can never take it off to begin with because it will be extremely reactive, unstable. So in order to do a substitution reaction on your alcohol, you can use tosyl chloride on it. So what essentially happens is chlorine will pair up with your hydrogen, so these two will be extracted, and that will mean that your tosyl group will be attached to your alcohol. Now this by itself is a good leaving group. Treat OTS, your tosylate ion, just like you would treat bromine, chlorine, iodine. Treat this like a good leaving group. Now the second step is telling me I'm using NaCN. So according to this, NaCN is going to be a strong nucleophile. So, since I have a secondary substrate and a good nucleophile, I can do a simple SN2 reaction. So I could have OTS leave and have it replaced by cyanide. Questions on this one? Yes?
You have to write out the plus OTS.
No, I'm just using this to indicate that this was like Br minus, I minus. This is just for you. You don't have to write it. Yes?
When would CN be?
When would
CN.
CN by itself? Let's say CN minus is your strong nucleophile. So let's say if I had a hydrogen, for example, attached to CN. Yeah. Just like how RO minus is strong, but ROH is weak. Make sense? Okay. Questions on this one? Yes?
So if we had this problem, we'd have to write out both steps.
You don't have to. You can just skip to the last step. You can just write this. Yeah. You don't have to write it. I'm just using this to tell you what happens over here. That's all. Okay. So part D. Over here, I have two bromines and the Ki. This is a special reaction that we're looking at here. This is actually going to be an E2 reaction. How can I tell? It's because I have two of the same leaving groups being exactly opposite to each other, meaning one is on a wedge, one is on a dash, and I'm using Ki. This could also be given to you as NaI or even LiI. So what is happening here is you're basically doing an A2 reaction. However, instead of your base taking off a hydrogen, it's taking off a bromine. So you're getting an iodobromide out of this one. So if I were to draw your product for you, I will be getting a double bond here. Just like an E2 reaction. One of the leaving groups leaves, and then my I minus is going to be taking off a Br. So I get an IBr out of this one, an iodobromide. Questions on this one?
Does it matter which of the bromines leaves?
No, doesn't matter. I use this one to just indicate that. So. Yes. Between the two bromines.
Why are neither one of the bromines on the product?
On the product?
Like once we do the E2 reaction, how come there's no bromine?
Oh, it's because, see, your I minus is going to be taking off one of the bromines, and one of the bromines is just going to be leaving by itself. So both of them will be taking off of the product. See, if it was an E2 reaction, you would have a bromine taken off by itself, it would leave by itself, and then you would have a hydrogen taken off by a base. Here, instead of a hydrogen, the iodine is taken off a bromine. So both of them leave in this case, not just one of them. Questions on this one? Yes? Well, on this one, because I'm using Ki, I'm forcing the reaction to take off both bromines. So Zaitsev and Hoffman, I don't care about it really on this one specifically. Okay. Question E. So one of you asked me that why aren't you doing an E1 reaction? How would I know I'm doing an E1 versus an SN1? Here's how. I see an alcohol, an OH attached to my hydrocarbon chain, and I have a strong oxy acid, like sulfuric acid, not a binary acid, not this guy, this, a strong oxy acid. So what is happening here is, this is a strong acid, right? So this is going to be deprotonating a lot. It will be giving me a lot of H+ ions. What's going to happen is one of these H+ ions is going to attach to the oxygen. So my oxygen will now have 2 hydrogens attached to it, which would mean that my oxygen should have a positive charge. Remember, this oxygen right now is extremely unstable in its structure. So what I can do is break this bond towards oxygen, forcing this guy to leave. Oh, sorry. Forcing this guy to leave as water. And then I will be left with a carbocation intermediate. From this point forward, it is your job to determine which hydrogen you should be taking off to form an alkene. Remember, the product of your elimination reactions is always going to be an alkene. This is an E1 reaction, so therefore the product should be an alkene. Okay? Now, I have 2 options. I can either take off this guy, or I could take off this guy. So remember, your E1 reaction compared to, let's say, an E2 reaction is going to be similar to an SM1 in the sense that it's a 2-step reaction. So the first thing that I should be doing is stabilizing this positive charge, okay, before I take off any of these hydrogens. So this positive charge right here, if I put it here, it will be secondary, sure, but it will be benzylic versus just this being a tertiary position. Any questions on this one? Okay, so that would mean that my positive charge should be here. And by doing that, I have no choice but to take off this hydrogen. So my final product will look like this. Very interesting. This carbon, this hydrogen. The alkene is between the 2.
Do you not have to stabilize before we take off any hydrogen?
Yes, you have to stabilize your positive charge just like you would in an SM1 reaction. Stabilize your carbocation, always, and then the hydrogen that you want to take off and form an alkene.
So you took the hydrogen that's right next to the phenol group.
Yes, because there is no hydrogen on the phenol itself.
So then the carbocation becomes on that, and then what's next?
Then I have to choose which hydrogen should leave for me to form an alkene.
I have to do that one.
Yes, remember, this positive charge on a carbon by itself is unstable. So the hydrogen leaving actually allows me to stabilize it by forming an alkene. That's why the hydrogen should leave. Okay? Questions on this one? Yes?
Why do you have it going like from the pH or the phenol? Why do you have it going down in your answer, like it's up in the original one?
It's the same thing. You could draw both of them. It's absolutely
It
fine.
doesn't matter
No,
on the
it's the
indication.
same. Yes?
Why did the charge goes to the left? Is it because of the benzene?
Exactly. It will be a benzylic position. It can resonate on the ring versus just being a tertiary position. Yes. There you go. Questions? Okay. Next one. So here on F, I have both an iodine and a fluorine, and both of them are secondary. However, my question to you, which one is the better leaving group, iodine or fluorine? Iodine, exactly. Therefore, this will be leaving. This will be my leaving group. The fluorine stays where it is. It won't leave. Now, my substrate is a secondary substrate. And let's look at this one. So K is just like Na, is just like Li. I'm going to just cross it off, replace it with a negative charge. And if I do that, I'll be left with N3 minus, which according to this is a strong nucleophile. So, since I have a good substrate and I have a good nucleophile, I will be doing an SN2 reaction. And like all my SN2 reactions, I'm careful to put this on a dash to indicate inversion for my SN2. Please don't forget this. This is a mistake a lot of students make. You forget inversion. Do not forget this. Okay? Questions on this one? Yes?
Why did you say it was SN2?
Oh, because the leaving group is on a secondary carbon. Secondary is fine for an SN2. So now we start looking at my nucleophile. My nucleophile is azide, N3 minus, and N3 minus is a strong nucleophile. So because I have both a good substrate and a good nucleophile, I'll be doing an SN2 reaction. Good. Okay. Question G. So again, like all of my questions, I will look at this. This is secondary. However, it's next to a tertiary carbon, which some of you refer to as quaternary. It's fine. So this isn't going to be a good substrate for me to do an SN2 reaction. And also, KOTBU is going to be a weak nucleophile, but a strong base. KOTBU is a strong base, weak nucleophile. So I don't have a good substrate or a good nucleophile. However, because this is a good base, I know that I can do an E2 reaction instead. So this would be an E2 reaction. Now, remember I told you if I use a bulky base, KOTBU, LDA, I'll be doing a Hofmann product instead of a Zaitsev product? Well, here's the thing. Remember, this isn't iodine, this is just ethyl. Yeah, some of you thought this was iodine, this is just ethyl. So your leaving group is just bromine. So here's the thing. I should be forcing a Hofmann product, right? But the thing is, I only form an alkene here. I can't even form an alkene. I don't have any hydrogens to take off. So Zaitsev and Hofmann in this question, it doesn't really make sense. However, remember that you're doing an E2 reaction. Okay? Questions on this one? Now, with all my questions, I always want to check for anti-coplanar. Always, I am checking for anti-coplanar before I do anything. So here, if this propyl group is on a wedge, this would mean that my hydrogen should be on a dash going up. If this hydrogen was on a dash going down, then this will be considered an anti-coplanar structure. Well, because both of them are pointing upwards, they're not going to be anti to each other. So I'm going to be so I will have to make a rotation on this one as well. So if I were to draw this thing out, let's say like this. I want this bromine to be, I don't know, on a line going up. That would mean that this hydrogen should be on a line going down. So let's go back to this. Right now, the bromine I have looks like this, and my hydrogen is this way, going away from it. So these two on a neon projection should actually look like this. So the bromine and the hydrogen should be anti to each other. Right now, that's not the case. Right now, this is what I have. Okay? So that would mean if I rotate my bromine, right now I have this. If I rotate my bromine to put it on the line, that will force the hydrogen to be on a dash going away from me. Hydrogen is on a dash going up. Now it will be on a dash going down. So that would mean that this big R chain should be on a wedge coming towards me. Now here, right now the hydrogen is on a dash going away from it. So if I turn it around, say it's on a line, that would mean that the methyl group over here should be coming towards me on a wedge. So that would mean that the propyl group would be on a dash going up. So if I form a double bond, I know that the big R chain and the methyl group will be on the same side. I think on your answer key, I missed this little methyl here. I didn't draw it, but it's here. Questions on this one? Yes? Like this. So if I were to draw out the R chain. Methyl, let's say ethyl, like that. And your hydrogen is here. But I don't draw the hydrogens here. Yes?
At the beginning, you said you'd be looking for a Hoffman product.
Mm-hmm.
I'm confused because in E2 reaction, wouldn't you be looking for Zysa?
Yes. However, KOTBU is considered a bulky base. If I were to draw it out for you, it will look like this. Potassium, tertiary TBU, butoxide. This is a bulky base. If I use a bulky base, I'm forcing the reaction to form the Hoffman product, to prepare the Hoffman product. But those two concepts won't really be applicable to this question. Because here, I don't have a choice but to take this hydrogen off. Yeah. Sure. Questions? Okay. Question H. So here I'm given two steps. So step number one is NBS and HB. So this is light. And this is signaling that I'm doing allylic bromination, NBS. So my double bond is right here. The allylic position will be here. So that will mean that my bromine should form right here. And then, let's take a look. We're using CH3 and in A. Remember, I told you, if you see these guys, just cross them off, replace them with a negative charge. So, two methyl groups, basically two R chains, attached to a negatively charged nitrogen. These classify as strong nucleophiles and strong bases. So, let's take a look at this. So right here, this bromine, is it on a primary carbon, secondary carbon, tertiary carbon? What carbon is it on? Yes, this is going to be a tertiary carbon. So because it's tertiary, I'm not going to be doing an SN2 reaction. But because this guy right here is going to be a good nucleophile, a good nucleophile and a good base, I will be doing an E2 reaction. So all I have to do here is just put a double bond. If I rotate it, if I make an anticoupling, if I do anything for you, it won't make a difference. Because the two methyls here, they're basically indicating that whether you rotate it around, it's going to be anticoupling for you. So you don't have to go through the pain of rotating this around or rotating that around or making that anticoupling. You could just try it like this. So any questions on this? Yes?
Well, why did you do that?
Okay, so this substrate was tertiary.
Oh, sure.
Yeah. Secondary is your last opportunity for an SN2 reaction. And since this was a good base, then I will be looking at an E2 reaction. Remember, I always look at my substrates. If it's good, then I look at the nucleophile. If that's good as well, I'm doing SN2. If one of them is off, then I start asking myself, is that a good base? If the answer is yes, it's an E2. If the answer is no, you're stuck with an SN1 reaction. Okay. Now part I. So over here, this bromine, is it primary? Is it on a secondary carbon, a tertiary carbon? What type of carbon is it on? So let's take a look. So right now, this is what I have, right? So this is my bromine attached to one carbon. So this carbon is attached to an ethyl group and a back carbon. So since I have two carbons around this, this is going to be a secondary carbon. So this is good for an SN2 so far. Yes, 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 yes. Oh, sorry. Yeah. Is that better? There we go. So this is a secondary bromine. This is good for an SN2 reaction. Now what about this guy? So if I have a thiol attached, so hydrocarbon chain attached to SH, hydrocarbon chain attached to SH, this classifies as a strong nucleophile. So since I have a good substrate and a good nucleophile, I will be doing an SN2 reaction. And also, this solvent is a polar A product solvent. So this is also hinting that you're doing an SN2 reaction. Now remember, on your Newman projection, if you're trying to show inversion of stereochemistry, what I advise you to do is change your two substituents with each other. So if I were to draw this, hydrogen, 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 I would attach my sulfur to the right side instead. And the hydrogen as well. Well,
It's still playing.
it's still playing on that one and this one, right? Check. Right now, I know this will work. Okay. Almost done with the reactions. Questions on these? Okay. All right, 3 more reactions. Let's see. So over here, so I have a Fisher projection. Remember, on your Fisher projection, your horizontal lines are indicating that they're on a wedge, and the vertical lines are on a dash. Now, with that in mind, let's take a look at this. So over here, what's going to be my leading group?
OT.
Yes, OTS. Remember, in the previous reaction I told you, OTS treated like it's bromine, treated like it's chloride, iodine, just treated like a good leading group. So with that in mind, let's go ahead and see if this is primary, secondary, tertiary. So this is my carbon. So this is attached to 1 carbon, 2 carbon. So this is going to be a secondary substrate. And with that in mind, let's go ahead and take a look at this. If this is a good nucleophile, I can do an SN2 reaction. So my amines by themselves, these are going to be classified as a strong nucleophile. So because I have a good substrate and a good nucleophile, I should be doing an SN2 reaction. Yes?
This is not tertiary C2H5.
So C2H5 is just going to be linear. See, C2H5 will look like this. If I had, let's say, this is my carbon attached, carbon, carbon, just like that. I don't have another carbon coming in from this. That's what I'm trying to say. See, 2 hydrogens here, 3 hydrogens here. So C2H5. C2H5 is indicating a linear effort loop. Yes? CH3, oh, solvent, well, your solvent isn't determining what reaction you do. It essentially affects the rate of your reaction, how fast you're doing it. Yes, it is. See, yeah, substrate is good, nucleophile is good, and also, this is a polar aprotic solvent. So this could also be hinting that I'm doing an SN2 reaction as well. Okay? So, on your Fisher projection, just like your Newman projection, what you have to do to show inversion of stereochemistry is switch your horizontal substrate traps. So what I will do is redraw this. You can also show it on a line angle diagram if you want to, as long as you show the correct answer, meaning that the chirality of this, whatever my product will be the same on your line angle diagram. You can show it on Fisher, you can show it on line angle, it's absolutely fine. So I know that this hydrogen will now be on the right side, and instead, the methyl group will be, let's just, my nucleophile will be on the left side. And this will allow me to inverse the chiral. Okay. Questions on part J? Good. Okay. So let's move to K. Now, on K, let's take a look at our substrate. Remember, in all of my questions, I've looked at the substrate, all of them. So this carbon is on a secondary, but it's next to a tertiary. So secondary next to tertiary, which you might know as quaternary, for example, this will be sterically hindered. So you can't do an SN2 reaction for this one. And also, your carboxylic acids are going to be classified as a weak nucleophile and a weak base. So this isn't good for an SN2 reaction. And since this is a weak base, I can't do an E2 reaction either. So I'm stuck with an SN1 reaction. My process of elimination, remember, it's always going from SN2 to E2 and then to SN1. This is the trend I've been following for all of your questions. So, just like every single SN1 question, I'm going to form my carbocation intermediate. So it's going to be right here. And I have the option of doing a methyl shift with this guy. So this will put the methyl group on a tertiary position for me. Sorry, the positive, the carbocation on a tertiary position and the methyl on the secondary. So I switched these two around. So if I do a methyl shift, this will be tertiary, and now I can do my nucleophilic attack. So my answer will look like this. So I just redraw my ring, methyl here. This attached to oxygen, attached to the carbon, like this. Questions on this? Yes.
How do we know that the carboxylic acid was the nucleophile, not methanol?
Oh, your nucleophile is going to be above your arrow, unless you're given like numbers. For example, number says number 1, you're doing this reaction. Number 2, you're doing this reaction. So, okay. All right. So, here I'm giving a chair, but it doesn't matter because if I draw it out, so the I is going down, that would mean it's on a dash, and then 2 carbons away, 1, 2, let's say here, an ethyl group on a dash. Okay, so this is a secondary iodine, and sodium methoxide classifies as a good nucleophile. So, since I have both a good substrate and a good nucleophile, I have to be doing an SN2 reaction. So if I redraw the chair, remember, inversion of stereochemistry on this carbon specifically will mean that whatever is attaching will now be on a wedge. So the methoxide will be going up axial. If you want to draw it two-dimensionally, this will be like this. There's I will go for a chair conformation if they're giving you a chair conformation. Yeah. There's purpose behind it if they're giving you a chair. Yeah. Ooh. Yeah.
Why is it, why can't it be E2?
Okay. So I start with my substrate always. It's a secondary substrate, right? And this is a good nucleophile.
Isn't that also a strong base?
Yes. However, remember my SN2 reactions, I'm always looking for a way to either do them or eliminate them. They're your fastest reaction, the most reactive reaction.
Okay, so SN2 would take part of the
Always remember, in all of the reaction questions I've done for you guys, I always started with SN2 and then moved on to E2 and then I moved to SN1. Always. Questions on the reactions?
Didn't you, is the like is it axial?
Oh, it's equatorial and going down. If it was axial, it would be a vertical line.
So I thought it was
See, this iodine right here, oh, I know what you're asking. See, transdiaxial would matter if you're doing an E2 reaction. Yeah. Here I'm just doing an SN2 reaction. Yeah. Okay. Moving on from question 6. All right. So let's take a look at number 7. So part A says to draw the major product of this guy right here. So again, I look at my substrate. Is it primary, secondary, tertiary? Right now, this guy is secondary. And I also have a good nucleophile. So because I have a good substrate and I have a good nucleophile, this will be an SN2 reaction. So I'm just going to redraw the ring on the left. And if I'm trying to attach my nitrogen here, remember, inversion of stereochemistry for SN2, so this will be on a dash, and H attached to pH. SN2, yes?
Wouldn't this be considered bulky? Like,
No. If it looked like this, it would be bulky. Okay, so SN2. And now it says, what would happen to the rate of this reaction? Remember, so I determined this was an SN2 reaction. Now with that in mind, what would happen to the rate of the reaction if my solvent, the MF, was changed to methanol? So it's telling me in an SN2 reaction, if I change my solvent from polar aprotic to polar protic, what will happen to the rate of my reaction? Would it increase or would it decrease? Yes, yes, it will decrease. So it will go down. Yes?
Isn't that nucleophile bulky though, because it's connected to this NH nucleophile? I thought this would have to be decreased because of how bulky that is.
No, that's not bulky. Remember, that's not like your cyclohexane. A phenyl ring is flat. Yeah.
It's not, a phenyl ring is not bulky.
No. Your phenyl isn't. But if I have 3 of them, then yeah, I'll consider that bulky. If I have 3 of them on the same carbon, yes, that will be a tertiary. Okay? Good question. So part C says if I change chloride to Br, so if I change my leaving group from chloride to Br, what would happen to the rate of my reaction? Yes, it would increase. Because, remember, your SN2 reaction depends on both your substrate and your nucleophile. So if I'm affecting the substrate by making it better, I'm increasing the rate of my reaction. No. See, on your periodic table, you go F, Cl, Br, I, AT, and so on. Br is larger in diameter compared to chlorine. So once it leaves as Br minus, it will be much more stable compared to chlorine because it can distribute the charge on a larger surface area. So it's a better rating. Okay. All right. So part D says, if I change my nucleophile to KOTBU, so it says, if I change my nucleophile from a good nucleophile to a bad one, that's a good base. What would happen to the rate of my SN2 reaction? Yes, it will go down. Remember, that is a good base, but I'm asking about the rate of my SN2 reaction. I'm not asking about E2. So because this is bulkier, the rate will climb. Now it says, what if my substrate was changed to CH3Cl? So what would happen to the rate then? Your rate should increase. Remember, this is basically a methylic substrate. A methylic substrate, which isn't as bulky as this guy. So your rate should increase.
Wouldn't this be connected to 3 carbons instead of 2?
This, no. See? This carbon has 4 bonds. 3 of them are to hydrogen, 1 of them is to chlorine.
But we're saying that it was on the secondary carbon.
Oh, okay. So you're saying if I put CH3Cl here?
Right, that's what it's asking.
No. The question is asking you if I change this entire thing to this.
Oh.
Yeah, if I go from that big group to this. Okay. Yes?
What I'm saying is I don't understand why number 7 can be SN2 because like aren't both the nucleophile and the substrate bulky in this one? Like those are both bulky. So like, how it's like sterically hindered. How can that be?
Your nitrogen isn't sterically hindered. It's connected to, let's see, 2 carbons linear to it, not branched, 2 carbons linear to it, and just to a phenyl. And here, this is secondary, and if this was, let's say, a tertiary, if it had another substituent attached to it, then you could count that as steric hindrance. Okay? All right. Now question 8 is telling me to draw the reaction energy diagram for this reaction. So let's first determine what type of reaction it is. See, this one, my leaving group is 1, 2 on a secondary position, and KOH, remember I told you cross this off. So I have a good substrate for SN2, and OH minus is a strong nucleophile. So because I have both a good substrate and a good nucleophile, I should have an SN2 reaction. Any questions on this one? Now remember, your SN2 reactions are going to be exothermic. So if this is my energy, and this is my reaction coordinates, you don't have to write this part. If my product, sorry, my reactant starts here, I will peak and go down this way. Remember, a couple of things I want to point out on the energy diagram. Number one, I have one peak, not two. Your SN1, your E1 would have two peaks because they're two-step reactions, because I'm forming n carbocation intermediates. But my SN2 and my E2 reactions are going to have one peak because they're concerted, a one-step reaction. They don't have any intermediates. Okay? And also, SN2 is going to be exothermic almost always, because what you're starting out with is really reactive. So by substituting these two, you're stabilizing them. So it's a win-win situation. I'm going from a bad leaving group to a good leaving group. Any questions on question 8? Okay. So that's that. I promise we're almost done. These guys. So these are going to be synthesis questions. They might look a little complicated in the beginning. You might think, well, what should I do? But in this exam specifically, since you haven't learned that many reactions, what you've learned is just bromination, SN1, SN2, E1, E2. You don't have that much diversity in the reactions you've learned, so I don't think you'll be given anything outside of these. Okay? So for example, this question says, if I want to go from here to here, what are the steps I should take? Now, I have given you this, well, kind of how many reactions you should be doing. For example, 2 arrows are indicating that you're doing 2 reactions. So let's work backwards. For example, on here, I'm adding ethoxide onto this location. So whatever it was initially, I had a good leaving group here, and I had O minus. Okay? So I know that this is what I had before I got this product. So what I should have on this place is a good leaving group, let's say like Br. So I know that before this, I should have had a good leaving group like Br. See, I'm working backwards in my synthesis. And here, this is a tertiary position, correct? And since I'm not forming any alkenes, I only have one alkene that's remained the same. I'm not doing any elimination reactions. So I'm left with either SN2 or SN1. Because this is tertiary, I know that this should be an SN1 reaction. Even though this is a good nucleophile, because this is tertiary, it should be an SN1 reaction. So that would mean that the solvent I'm choosing should be polar protic instead of polar aprotic. Something like, let's say, methanol, water. Questions? Remember, this is called retrosynthesis. I'm going backwards. Now, from here, if I want to go from this substrate to this product, what type of reaction should I be doing? How do I add the bromine there? Yeah, bromination. And to be specific, it's allylic bromination because I'm putting it in an allylic position. So I know I should be using NBS NH. You could use heat as well. It's okay. You don't have to always use light. You could use this or just triangle. Any questions on the synthesis on part A? Okay. Second one might be a little complicated. Okay. So I have gone from a 1, 2, 3, 4, 5 member ring to a 1, 2, 3, 4, 5, 6 member ring. So I know that during the entire process that I was doing this reaction, I was doing ring expansion. Okay? So I was doing a ring expansion. Now, where did that happen? Well, based on the information I provided, it must have happened on this step specifically. Because I've gone from a 5-member ring to a 6-member ring. So, which reaction had ring expansions involved in it? Was it your E2 reactions, your E1s, your SN1s, your SN2s? Which? Yes, an SN1 reaction, exactly. So I know that whatever I'm using should be a polar protic solvent and a weak nucleophile. So for your weak nucleophile, let's say I use an alcohol. Now, would that be correct?
No, you need to force it. You need the like AG or something.
So yes, you're right. But more importantly, if I used an alcohol, I wouldn't be getting an iodine. So let's say over here I use an AI. Because even though this is a good nucleophile, this will be an SN1 reaction. Because over here I have 1, 2, 3, I have a tertiary attached to this primary. So this will be primary next to tertiary. And because your I minus is a good nucleophile but a bad base, I can't do an an E2 reaction because this is a bad base. It's just a good nucleophile. So for your solvents, you know that you should be using a polar product. Let's say this time I use water. Anything works. So what happens here is leaving group leaves. I get a positive charge here. And then if I break this bond off and form it here, that will mean that this carbon is the same carbon, it's going to be this carbon right here. So because I'm breaking this bond with this carbon specifically, the positive charge will be on this guy. So it should be here. Questions on this one? Yes?
Do you also have to do like a method shift or something so that you can put that metal substituent on the left?
Why do I need to? See, if I break this bond, I'm introducing a positive charge on this carbon. Okay? Now, this carbon, once it bonds up with this carbon, it will neutralize this charge. So, by breaking this bond and expanding it, I'm automatically putting this positive charge on the carbon with the methyl.
I just mean like in the second step, the metals are on the left side.
Yeah, I could number them for you too. Let's say this is carbon 1, 2, 3, 4, 5, and 6. So I know that carbon 2 will have a methyl. So let's go like 1, 2, 3, 4, 5, 6. So I know that carbon 2 should have a methyl. Carbon 3 should have 2 methyls. 4 and 5 have nothing. Carbon 6 should have 1 methyl coming off. If it confuses you, label your carbons. You can number them if you want. Okay? So here I did an SN1 reaction. I did a ring expansion. Now from here, I don't know where I'm going, so I'm just going to take a look at this part now. Let's do retrosynthesis. So over here I had a leaving group. I went to an alkene. So which reactions give me alkenes? Is it elimination reactions or substitution reactions? Elimination, yes, exactly. So over here, because I don't have an alcohol, I know that I was doing an E2 reaction. Okay? So if you want to do an E2 reaction here, what you have to do is use a strong base. Let's say like NaOH, like KOH. I'm gonna do KOH. You could use any of these guys. Any of them. Okay. All right. Now, this is fixed. So what would I have to do to get to this part? Remember, here I formed an alkene that originally wasn't here, right? So that would mean that from this step to this step, I had to put a bromine over here. So from here, I added a leaving group. I added a leaving group. And here I formed an alkene. Okay? Now remember, if this double bond is going to end up being on the top, what will I have to use? Remember, if I choose this hydrogen to take off, my alkene will have 1, 2, 3 substituents. So that will mean here I formed a Hofmann product. So what type of base was I using to form a Hofmann product? Yes, a bulky base. So let's say something like LDA. This is what would give me the alkene. And then from here, the difference between these two is the presence of a bromine. So the bromine is on an allylic position, and because of that, I know what I can use to put it on an allylic position is N-bromosuccinimide with light or heat, whichever one you prefer. Questions on this? Yes?
Would you mind explaining the ring extension one more time?
Of course, of course, of course. See, what I was saying is, initially I saw this was a primary, right? But since it was next to a tertiary, I knew this was a bad substrate to begin with, okay? And also, because I knew this was a 6-member ring, I did a ring expansion, and the only reaction that allowed me to do that was my SN1, okay? So, I knew that I was doing an SN1 reaction, but I knew that my nucleophile had to have iodine on it, because I was replacing chlorine with an iodine. So I just used like sodium iodine or potassium iodine, anything we can, okay, as long as it has this guy. And I knew it had to be polar, like water or methanol, either one of the one. Okay. Now, for your ring expansion, leaving group leaves. I get a positive charge right? So what's going to happen is I'm going to break this bond off, and I'm going to reform it between these guys, like this, okay? So breaking this guy off introduces a positive charge on this one and a negative charge on this one, okay? And formation of a bond between these two will neutralize this positive charge, okay? So I know that my positive charge will be on the carbon that has one methyl next to 2 methyls. That's how I knew the iodine was going to be attaching to this carbon specifically. So all I did was draw a 6-member ring, since I know I'm going from 5 to 6, and then you can label carbon number 1, 2, 3, 4, 5, and 6. So I knew that carbon number 2 would have a methyl on it. So let's say this is 1, 2, 3, 4, 5, 6. 2 has a methyl. 3 has 2 methyls. 4 and 5 have nothing. So 4 and 5, nothing. And then carbon 6 has to have a methyl group attached to it. Wait a minute, did I mess with this? Let me make it a little bigger. There you go. 1, 2, 3, 4, 5, 6. Okay. So carbon 2 had my methyl on it. Carbon 3 had 2 methyls on it. 4 had nothing. 5 had nothing. And then 6 would have this carbon. Like this. Okay? So I said that my positive charge would be on carbon 2. So carbon 2. So I would know that my iodine will be attaching to this position specifically. This is the same as this. I appreciate you guys staying. I know it took a long time. I appreciate you guys staying. I hope that this was helpful for you guys. If you have any questions, please feel free to ask me. I'll answer all your questions. Sami, thank you so much. I appreciate it.
So for 5C,
5C.
I think if we use
Okay. 5C.
so wouldn't you, acid one reaction, wouldn't you go for the tertiary carbon?
So, good question. See, the thing is, putting this here as someone will mean that I'm making this alive. This is going to be resonance stable. This will be much more stable for a positive charge compared to just the tertiary.
This resonance right here?
Yes.
And can I also get a picture of the chart?
Which, yeah, of course, of course. Take a look.
And then one more question.
Sure, sure, sure.
For question 9, when you had
Can I take a picture?
Yeah.
when you had NBS to it, wouldn't you for the tertiary? I was
It's allylic. NDS is allylic combination. And also the same like the radical will be resonance stable as compared to tertiary.
yeah.
It's the same like.
Okay.
You're welcome. Let me just stop recording this.
Thank you.
Yeah, sure. Okay. Sami,